Without a doubt, Juno is one of the most important missions that NASA has ever launched. This is a probe that defied the odds, surviving for years past its original mission end date in a region of space that is usually deadly to probes. It is NASA's most distant planetary orbiter, investigating our solar system's largest planet. And what it has learned there has shaken our understanding of everything we thought we knew about Jupiter. Its formation, its composition, and the mechanisms that give it such a powerful magnetic field. But Juno didn't stop there. It has investigated Io, Ganymede, and Europa. It has studied auroras and the largest volcanic eruptions we've ever seen in our solar system. And as this incredible probe has reached the conclusion of its extended mission, it's time to ask the question, what has Juno seen? I'm Alex McColgan and you're watching Astrum. Join me today in this supercut as we explore the discoveries Juno has made around Jupiter over the years. And like all good stories, this is a tale that ends with a twist. So let's start from the beginning. As far as NASA missions go, Juno is a medium budget project with total expense that was initially expected to be about $1.1 billion over the course of its mission time. Now, Juno is a massive spacecraft, 20 meters in diameter. And it really has to be, because unlike previous probes we've sent out that are powered by radioisotope thermoelectric generators, Juno is a solar-powered spacecraft, and it only gets 4% of the sunlight it would do around Earth. This means that even though these panels are huge, it can only generate just above 400 watts. It was launched on the 5th of August 2011 using an Atlas V rocket. Escaping Earth's atmosphere and entering orbit is one of the most risky parts of the whole mission, but everything went smoothly, and less than an hour after liftoff, it was already on an escape trajectory from the Earth. Juno's journey to Jupiter was an interesting one, as after it escaped Earth's gravity, it headed into deep space. At this point, it did a small burn using its engines and headed straight back to Earth, reaching it 2 years after it had first launched. You may wonder to yourself, why would they do that? Well, the answer is very clever. When Juno reached Earth again, the gravity of Earth started pulling Juno towards it. This gravitational influence increased the speed of Juno by over 14,000 kilometers per hour, slingshotting it at top speeds towards Jupiter. This method is more fuel efficient than burning the probe's engines to get there. After a monumental 5-year journey spanning 2.8 billion kilometers, Juno entered orbit around Jupiter in 2016. Its primary mission consisted of 33 polar orbits of the gas giant. At its closest approach, flying only 4,200 kilometers above the Jovian atmosphere. Being this close to Jupiter is a big problem as far as delicate scientific instruments go. You see, Jupiter has an extremely powerful radiation belt around the planet, easily powerful enough to fry most electronics. Do you remember the previous Jupiter probe, Galileo? Galileo faced a number of setbacks due to the damage received by Jupiter's radiation as its orbit went right through the middle of the radiation belt. So mission planners were keen to avoid a repeat of that as much as possible. Being this close to the planet means Juno would go straight through that deadly radiation belt. This is why the expected mission life of the probe to begin with wasn't over 20 months in orbit, with some instruments not expected to last beyond the first 8 to 9 months. To try and prolong the inevitable, Juno was surrounded by a 1 centimeter thick layer of titanium to protect the internals from frying. It's kind of like a tank going into space. But whether this would be enough or not was something that scientists were initially uncertain of. So what about Juno's mission? Well, sadly, the initial plan was for Juno to not turn its attention to any of the moons, but instead focus on Jupiter itself. It would measure the amount of water in Jupiter's atmosphere to determine which planet formation theory is correct. It would look deep into Jupiter's atmosphere to measure composition, temperature, cloud motions, and so on. It would also map Jupiter's magnetic and gravity fields. We already know the magnetic field of Jupiter is hugely interesting due to its strength and size. Did you know, for example, if the magnetic field of Jupiter was visible in our sky, this is how big it would appear? Juno would particularly explore and study Jupiter's magnetosphere near the planet's poles, especially the auroras, Jupiter's northern and southern lights, providing new insight into how the planet's enormous magnetic field affects its atmosphere. In this way, Juno would follow closely after its namesake. Juno's name comes from Greco-Roman mythology. The god Jupiter drew a veil of clouds around himself to hide his mischief, but his wife, the goddess Juno, was able to peer through the clouds and see Jupiter's true nature. An apt name indeed. On the 5th of July 2016, Juno successfully arrived at Jupiter and inserted itself into a polar orbit. It adopted a perpendicular orbit which brushed over the planet at its closest approach, only 4,200 kilometers above Jupiter's atmosphere at its perigove and 8.1 million kilometers at its apogee. The perigove is the point of a spacecraft's orbit when it is closest to Jupiter, and an apogee is just the opposite. It's the point in an orbit when the spacecraft is furthest away from Jupiter. Each orbit took 53 days to complete, and NASA's original plan for Juno was for it to complete its 33 orbits by the end of its mission in 2018, with a burn along the way to take Juno into a close 14-day orbit towards the end. However, this burn was later cancelled, as it was deemed safer, so Juno stayed in its longer orbital position until 2021. For all the worry over Juno's longevity, however, it turned out that there was nothing to worry about, due in part to a surprising discovery Juno made upon entering Jupiter's magnetic field. One of the reasons Juno approached so close to the planet was to avoid Jupiter's powerful radiation belt. But there is a gap where the planet ends and the radiation belt starts, and Juno threaded the needle to exploit that. There was some concern that Juno would still get a huge dose of radiation from the parts of the radiation belt it did hit, but the radiation was actually 10 times lower than expected in these parts. Great for the health of the probe. This was a stroke of luck for NASA, for Juno, and for us. Of course, another advantage of the tiny distance from Juno to Jupiter at its closest approach is that we have been able to see Jupiter in unprecedented detail. The first images of Jupiter's poles in particular took people's breath away. Some even say that scientists would not have even recognized the planet from these images. Just no one expected what they saw. What you are looking at here are many cyclones around the South Pole. What is remarkable is that the planet looks so different from what we are used to seeing on Jupiter, namely its large bands. However, in this image, the contrast has been increased to see details. The natural eye would see something more like this. This image is also a mosaic of several images in order to show daytime on all sides of the planet. The North Pole isn't quite so clear, as it's in winter and some parts of the pole are in constant night. Juno also has the capability to peer deep into Jupiter's atmosphere using a microwave radiometer, which was designed specifically for this spacecraft. Using it, scientists were able to see the amount of ammonia in the atmosphere. What they didn't expect to see was this band of ammonia around the equator, ammonia being orange in this image. The pillar drops down from the cloud tops over 350 kilometers, the limit of what the MWR can see. Scientists were puzzled by this, as they expected to see an even distribution of ammonia throughout the planet. They thought the gases in the atmosphere would just mix up, or at least stick to the band pattern of the planet. But these results were far from that. This shows how variable the planet is under the top layer of clouds. But one of the biggest revelations about Jupiter was not its cloud cover, but something much deeper. For decades, scientists argued what the core of our biggest gas giant was like. Was it solid or missing altogether? And in 2017, NASA's Juno mission made that debate irrelevant overnight. The data from Juno suggested both sides were wrong and revealed a third option no one expected. Jupiter's core isn't solid, but it isn't absent either. It's fuzzy. And that's a problem, because it upended everything we thought we knew about Jupiter's formation, its interior, and even its bizarre magnetic field. Let me explain. For decades, two competing theories dominated the scientific conversation around Jupiter's core. Many supported the gravitational collapse theory, which suggests that Jupiter formed directly from the collapse of a gas cloud under its own gravity. This would have happened in the colder, outer reaches of the solar system before Jupiter migrated to its current location. In this scenario, the gas giant would have no core at all. It would simply be a layer cake of churning gas all the way through. But this theory didn't have the whole scientific community convinced. Others were almost certain Jupiter's core was solid, made up of heavy elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. As this solid core grew larger and larger, its gravity started capturing more hydrogen and helium, swirling it together over millions of years to form the planet we all recognize today. Intuitively, this seems to make sense. Our solar system formation models suggest giant planets could be created this way, since ice and rock would condense first in the outer solar nebula, capturing gases in their gravity as they migrated inward. This theory, known as the core accretion model, predicted a dense, well-defined core with a clear boundary separating the compact center from the surrounding layers of gas. To resolve the debate, early missions to Jupiter all took their turn trying to discern what lies beneath the red giant's dramatic atmosphere. By the 1990s, scientists knew that Jupiter was rich in heavy elements, implying the planet was made of more than just hydrogen and helium. The Galileo mission also found evidence that Jupiter's magnetic field must somehow be generated by liquid, metallic hydrogen in its interior. But if the core is purely liquid, how did Jupiter form in the first place? The standard theory of planetary formation requires a solid nucleus to start gas capture. If Jupiter once had such a core, but somehow lost it, how did that happen? Could everything we know about how gas giants form be completely misguided? Despite the successful missions to Jupiter, the planet's structure remained a mystery. The data gathered wasn't precise enough to determine whether its core was solid or diffuse, what it's made of, or how exactly it generates such a massive magnetic field. But that all changed thanks to Juno's discoveries. Unlike Galileo that had gone on before it, Juno was purpose-built to map the planet's gravitational field in great detail, about 100 times better than previous maps. When it entered orbit on the 4th of July 2016, it began tracing a highly elliptical orbit, swooping down again and again from several angles, a path that made this probe incredibly sensitive to tiny changes in Jupiter's gravity. But why are we interested in gravity in the first place? What did that have to do with figuring out what Jupiter's core is made of? Well, we've all seen gravity depicted like this, a perfectly round cone, the same on all sides. I'm sorry to tell you, this diagram is a bit of an oversimplification. For a planet's gravity to be completely uniform like this, the distribution of mass inside it would also have to be perfectly uniform. In reality, if you zoom in really close, their gravitational fields look a little more like this. Planets are made up of many different elements and materials, each with their own masses, densities, and distributions. These differences are reflected as tiny, almost imperceptible variations in a planet's gravitational field. That's why Earth's gravitational field is actually slightly different over mountains than plains, and why scientists are so fixated on mapping Jupiter's gravitational field with incredible precision.
As Jupiter's gravity fluctuated, it caused Juno to speed up or slow down. The spacecraft was so precise, it could detect changes in speed as subtle as 0.01 millimeter per second. At the same time, Juno was continuously beaming a steady radio signal back to Earth, which scientists could decode using the Doppler effect. Where gravity was stronger, Juno accelerated and we perceived a higher frequency wave, while a deceleration due to weaker gravity resulted in a lower frequency wave. By repeating this over and over, scientists built up a very precise map of Jupiter's gravitational field, which directly reflects how its mass is arranged inside. While the Galileo mission managed to paint Jupiter's gravity in very broad strokes, Juno brought it into razor-sharp focus. And what it revealed about Jupiter's core caught researchers by surprise. As I said, it turns out both theories about Jupiter's core were wrong. It seems to have a core, but it isn't solid like we thought. It's fuzzy. Instead of a dense, compact ball, it's dilute, gradually blending with the hydrogen-rich layers above it. It doesn't appear to have any sharp boundaries. It's also much wider than expected, spanning about half the radius of Jupiter itself. The findings quickly sparked a flurry of questions, including whether our understanding of how Jupiter formed needed a refresh in light of this exciting new data from Juno. A popular theory soon emerged to explain this unexpected discovery, that Jupiter once had a solid core to begin with, but a catastrophic collision in its early history shattered and scrambled it in with the surrounding lighter gases to give us the fuzzy core we see today. The only problem is, our standard model for how giant planets like Jupiter form doesn't work without a solid core. So either Jupiter's fuzziness somehow developed later on, or our models are wrong. Anyway, for such a dramatic shattering to occur, the collision must have been massive, possibly with another young planet. Scientists speculate that up to half of Jupiter's core could have originated from the remains of this planet. It was a neat enough theory, except for one unexpected hiccup. A curious team of researchers tried to model this giant collision using a supercomputer. They wanted to emulate the exact event that would lead to the results Juno showed us. So they designed several possible scenarios of a massive object colliding with a Jupiter-sized planet and ran multiple simulations, varying the size of the Jupiter protoplanet and the angle and speed of collision. But try as they might, they couldn't find an event that led to the fuzzy core Juno showed us. Every time they tried, the models did the same thing. The impact would initially rock the planet to its core, but after a while, the dense, rocky material would settle back down again, like sediment at the bottom of a glass. It didn't dissolve into the rest of the planet. A sharp boundary would reappear, clearly separating the core from the outer hydrogen layers. It didn't fit the Juno data, so it was back to the drawing board. Funnily enough, the next clue in this puzzle didn't come from Jupiter at all. It came from its next door neighbor. Well, that is if you consider 648 million kilometers away next door. We've known since 2014 that the waves in Saturn's rings are caused by vibrations inside the planet. This gives us an insight into what the planet's core might look like, similar to how earthquakes let us study Earth's interior. When researchers paired Cassini's gravitational field data with these wave measurements, it painted a staggering picture. These observations show that at least some of Saturn's deep interior doesn't convect. This is a big deal. Inside a giant planet like Saturn, heat is constantly trying to escape. Normally, that happens through convection. It's what is constantly happening in Earth's mantle, or when you heat up a soup. Hot fluids rise to the surface, cool, and then fall back down, only to be heated up and rise again. On and on it goes. If Saturn were fully convective, it would mix heavy elements throughout its interior, there wouldn't be a dense central region at all. The whole thing would be a fully mixed, homogeneous soup. But if it were partly stable against convection, we'd expect to see a gradient of material, with heavier elements concentrated towards the center and tapering outward. And that's exactly what the data shows. Researchers published their findings in 2021, arguing that the only way to explain Saturn's ring wave data, gravitational field data, and partial lack of convection is that it too has a fuzzy core. As it happens, Juno data also suggests large regions of Jupiter may not be convective. We seem to be slowly connecting the dots. If Saturn and Jupiter have fuzzy cores, they likely stem from a common denominator rather than a random collision event. Now, scientists are working on a new, emerging theory of how the gas giants came to be, one in which fuzzy cores are a natural part of planetary formation. We haven't arrived at a neat explanation yet, but it is clear that the old assumptions we had about the largest planets in our solar system are incorrect. Jupiter and Saturn are not made up of solid core and gas envelope, nor do they have a completely mixed interior. Their fuzzy cores are made up of a compositional gradient, with more heavy elements concentrated in the center, which dissolve out into the gas envelope without a clear boundary. This complexity and uneven mixing challenges our current models for planetary evolution. Where our old, simplistic model predicted the giants would cool predictably over time, these new models don't follow the same patterns. And the same is true for all the gas giant exoplanets we've discovered and studied so far.
So Juno was already throwing out everything we thought we knew about Jupiter, including the very way these massive gas giants formed. Incredible. One of the biggest surprises to scientists came from Juno's magnetic field data.
For years, scientists have known that Jupiter's magnetic field is generated through a dynamo process in its metallic hydrogen layer. This layer spans 20 to 60,000 kilometers deep, where temperatures can exceed 30,000 Kelvin and pressures are millions of degrees greater than on Earth's surface. Under these extreme conditions, hydrogen is in a liquid state, but even more incredibly, here, hydrogen's electrons become delocalized or free-flowing. This creates an electrically conductive metallic state. Coupled with Jupiter's fast rotation, this metallic liquid hydrogen creates a dynamo effect, though the exact process of how it's powered remains a mystery. Whatever it's doing, it's working. Jupiter has the largest, strongest magnetic field of any planet in the whole solar system. Its magnetosphere spreads 7 to 21 times the diameter of Jupiter, tapering into a tadpole shape behind it that extends into Saturn's orbit, about 1 billion kilometers away. However, Jupiter's magnetic field also has some quirky characteristics. It's much stronger in the northern hemisphere than the southern hemisphere, has intense, localized magnetic spots, and 2 magnetic south poles. Scientists hoped Jupiter's fuzzy core might actually explain some of these strange behaviors. Frustratingly for them, the opposite turned out to be true. Jupiter's fuzzy core actually complicates rather than explains its magnetic field. Magnetic fields in planets are usually created by swirling motions of electrically conducting material, like the metallic liquid hydrogen in Jupiter's core. However, Juno data showed that large regions of Jupiter, like Saturn, seem to be at least partially non-convective. Researchers modeled the fluid dynamics of Jupiter's interior in 2 potentially non-convective regions to see how they would affect the magnetic field, one in the upper part of the planet's interior and the other lower down, corresponding to the dilute core. They concluded that the upper stable layer helps explain Jupiter's magnetic field even better than previous solid core models. However, the lower region, representing the non-convective dilute core, did not explain Jupiter's magnetic field on its own. In other words, a completely stable fuzzy core produces a magnetic field that's very different from the one we actually observe. Now, researchers believe Jupiter's dynamo is more complicated than originally thought. It's possible that below the uppermost molecular hydrogen layer, Jupiter has a layer of helium, which rains down through the liquid hydrogen, like oil passing through water. Some think this could have an effect on the magnetic field. Another theory claims Jupiter's dynamo doesn't operate in a homogeneous way like it does on Earth, and that instead, the planet's lopsided magnetosphere is the result of variations in density, electroconductivity, or both. But on the whole, no one knows exactly how this magnetic field is produced, or what role the fuzzy core plays in its creation. One thing we do know for certain though, is Jupiter's magnetic field is responsible for the biggest, brightest auroras in the solar system. On Earth, auroras are only visible for a 4 to 6 month window. On Jupiter, they never stop, covering the poles with a dazzling display of colour hundreds of times more powerful and energetic than the auroras we're familiar with. By stringing together far UV images from Hubble's imaging spectrograph, scientists were able to create these videos of the auroras in action. Aren't they spectacular?
Like Earth, aurora appear as bands around the north and south poles. But unlike Earth, these auroras are mainly visible in the ultraviolet and are mainly produced from alternating currents, not direct currents. When Juno measured the power generated from the direct currents in Jupiter's magnetosphere, it was nowhere near enough to account for the brightness of the aurora, leading scientists to speculate that the remainder of the power is coming from alternating currents. At this time, it is believed that these alternating currents are produced because of the turbulence in the magnetic field. Especially at the North Pole, the magnetic field lines are much more complex, which interferes with a direct flow of currents. This is evident when comparing the North and South Pole aurora. At the North, the aurora is much more dispersed, looking more like filaments and flares, whereas at the South Pole, where the magnetic field lines are smoother, the aurora seems to be more structured and round. Let's look at these auroras in another way. Juno has an infrared aurora mapper, giving us a view of Jupiter's auroras like we've never seen before. The whites and greens from this image are ions striking Jupiter's ionosphere from space, and the reds could be ions coming from the planet itself. If this is the case, it has never been observed before. What you will notice is this bright spot and tail in the aurora. This is visibly where Io's electromagnetic influence meets the planet. What is slightly less apparent though are these other spots. These are from other large moons in the Jovian system, Europa and Ganymede. So while not as powerful as Io's influence, these other moons have their own fingerprints connecting them to the planet too. Most of this data collecting took place for only a few hours per orbit as Juno whizzed by the planet. All the instruments collected as much as possible during this time, including the camera. This remarkable video is a time-lapse of Juno approaching the northern hemisphere and leaving again as it looked towards the southern hemisphere. And this image is a collection of all the frames that were used in the video. As Juno approached the planet, you can see the storms around the North Pole, and gradually the view shifts to the mid-latitudes. Zooming in on some of these shots, we can see the classic swirls and patterns we expect on Jupiter. But having a really close look, we can see these white specks. These specks are actually water or ammonia ice clouds, as can be seen by the shadows they create. They are higher in the atmosphere than the rest of the cloud layer, and although they look small, they are actually over 50 kilometers wide. Jupiter is just really big, so it looks small. Now you've noticed them once, you'll start to see them everywhere. Many of these discoveries were made early on in Juno's mission, and fortunately, as the halfway mark for its planned number of orbits approached, there proved to be more and more to uncover about Jupiter. While we knew about Jupiter's radiation belt, Juno completely surprised scientists by also discovering a small and less powerful radiation belt right above the equator, which hugs the planet tightly. So far, the mechanisms behind this radiation belt are unknown. But there were also more discoveries about Jupiter's large ring of radiation. Jupiter is surrounded by a large donut of charged particles. The particles in this plasma torus, as it is called, come particularly from the volcanic activity of Jupiter's closest large moon, Io, which blasts particles into orbit around Jupiter. Just to give you an idea of how volcanically active Io is, this was New Horizons' view of Io as it passed by Jupiter on the way to Pluto, the Tafashtar volcano in a full eruption. Juno has also had a look at Io in the infrared, the hot spots indicating where volcanic activity is occurring. Io ejects 1 ton of particles into orbit around Jupiter per second. As Io travels through the plasma torus and interacts with Jupiter's magnetosphere, this causes a flux tube to exist between the planet and the moon. A flux tube being an electrical current that travels along a cylindrical tube of magnetic field lines. It is very powerful. It can develop up to 400,000 volts and 1 million to 5 million amps of current. Juno was able to get very accurate readings of the flux tube during its 12th orbit as it passed directly through it. No, this didn't fry the spacecraft, as the flux tube has a large diameter, and so it isn't concentrated enough to do damage to the craft. Also, Juno was in and out in a matter of seconds. Juno was well equipped to study Jupiter's magnetosphere. You'll notice that this design, paired with the fact that Juno rotates, makes it a little like a fidget spinner. This isn't just to make a pretty spinning spacecraft. Juno was specifically designed to detect various fields and particles around Jupiter, and having a spacecraft with a large, spinning radius helps with that. This is particularly evident with this instrument here, the magnetometer found at the end of one of the solar panels, tasked with mapping out Jupiter's magnetic field. Through Juno's data, we now have a highly detailed map of Jupiter's magnetic field, which became more accurate with every passing orbit. As expected, Juno confirmed that Jupiter has a dipole-like magnetic field, although it is not very aligned with the rotational axis. What was very interesting though, is that scientists discovered something called the Great Blue Spot, a region on Jupiter where the magnetic field is very concentrated. Comparing Juno's magnetic field data with previous Jupiter missions like Pioneer, Voyager, and Galileo has also revealed a first for the solar system. Jupiter's magnetic field structure has been found to change very gradually over time, which is called secular variation. Interestingly, this was most apparent around Jupiter's Great Blue Spot. This variation is thought to be driven by a region right at the base of Jupiter's atmosphere, which we'll get to in a bit. One factor for the strength of the magnetic field is due to the rapid rotation of Jupiter. One day on Jupiter only lasts about 10 hours. Various forces from this stir the liquid up, which generates Jupiter's internal dynamo. Interestingly, it is the rotation of the magnetic field from which we can measure a day on Jupiter, as simply viewing Jupiter's visible bands couldn't give you a definitive result. And this is why. You'll notice that these bands look very peculiar, moving in opposite directions from each other at different speeds. But this isn't so unusual if you also consider the invisible jet streams on Earth. What is striking though, is the colors and turbulence found in these bands. So let's try and understand what's going on from examining these Juno images. The cloud layer you are seeing here is the ammonia cloud layer. Some are white. These represent fresh clouds likely only recently pulled up from the deeper parts of the atmosphere. On the other hand, while the red colors you see are also ammonia clouds, these clouds have interacted with UV light from the sun. Think of it like a photochemical smog, the reddish smog you see in summer over large cities. The coloring substance isn't exactly known, but simply put, the longer it is exposed to the sun, the redder it gets. Interestingly though, comparing these bands to what you see at the poles, you'll notice it is a lot bluer here. This could be because UV light doesn't reach here as easily compared to the equator. Looking closely at Jupiter, you'd be hard-pressed not to notice the stunning vortexes and storms across the planet. And Juno had the opportunity to orbit directly over the Great Red Spot, where it discovered something very interesting. It was known that the Great Red Spot rises high above the cloud deck, but what scientists didn't expect is how deeply it penetrates Jupiter's atmosphere. The instrument on board Juno designed to peer into the atmosphere had a range of 350 kilometers, and it seems that the Great Red Spot extends down even further than that. Also interesting is that the spot is cooler than the surrounding area up until a depth of 80 kilometers, and beyond that it actually gets warmer than the surrounding area, this heat perhaps driving the storm. It has been theorized that the Great Red Spot is a permanent feature on Jupiter, but we've only had about 400 years to observe it so far, a mere blink in astronomical timescales. Looking over the poles, other possible permanent features have been observed. In contrast to Saturn, which has a hexagon on one pole and a single vortex on the other, Jupiter has 5 vortexes around the South Pole and 8 around the North. It's hard to say exactly how permanent these storms are, as Juno has only been there for 3 years at this point of the video, and Juno was the first time we have really been able to have a look at Jupiter's poles, but they have been reasonably constant throughout that time. Under the ammonia cloud layer is thought to be a water ice cloud layer, although this has not been confirmed, as this layer hasn't actually been seen yet, even by the end of Juno's mission. This had been one of the science goals of Juno though, and it had several microwave detectors to try and find this elusive substance. Jupiter generates heat from within, which can be seen through an infrared camera, the densest parts of the cloud layer blocking some of this heat from being visible. Similarly, Jupiter also emits microwaves, which hypothesized water clouds would absorb. So in theory, Juno should have been able to detect where the water is present in Jupiter's atmosphere by searching for where Jupiter's microwaves aren't visible, although this data has either not been released or nothing has been found yet. By 2021, Juno was reaching the end of its original planned 33 orbits of Jupiter. However, scientists were delighted to discover that the probe was still going strong. The radiation Juno encountered had done minimal damage to Juno's hardware, and even its camera was still functioning, which was one of the first pieces of equipment expected to fail. Waste not, want not, as the old saying goes. So when scientists realized that their probe was still in excellent condition, rather than send it to its pre-planned demise, crashing into Jupiter's atmosphere, they extended Juno's mission for an additional 42 orbits. Excitingly, Juno would now extend its view to not just the planet, but Jupiter's moons too. So, what did Juno see there? On the 7th of June 2021, Juno performed its close flybys of Ganymede, using a gravity assist to bring its orbital period from 53 days down to 43 days. Juno had already performed a distant flyby of Ganymede in 2019, when it reached a proximity of 97,000 kilometers, but this one brought the probe within just 1,000 kilometers of the moon's surface. In this photograph captured by JunoCam, you can see nearly half of Ganymede's total surface in breathtaking detail. For reference, the resolution is about 1 kilometer per pixel. I love the crisp rendering of Ganymede's unique structural features. You can practically feel its texture with your fingertips. Notice how the icy surface is littered with craters, light and dark patches, and long striations. The darker areas show older terrain, which is heavily cratered, whereas the lighter areas are comparatively younger and less cratered. But what about those long striations? We know, based on previous data, that Ganymede contains at least one vast, salty subsurface ocean beneath its icy outer layer, which some speculate could be suitable for life. Scientists think that these long structural features
might reveal faults produced by tectonic movements generated by heat from the moon's iron-nickel core, but this is a subject of ongoing research. This image, taken from the same flyby on the 7th of June, shows Ganymede's Tross crater in greater detail. The reason it appears so bright is that it's covered in ice. Here is another image from the 7th of June which I find remarkable. It's a photograph of Ganymede's dark side, and it was taken by Juno's Stellar Reference Unit navigation camera. The Stellar Reference Unit was designed to keep Juno on course using starlight, which makes it ideal for photographing low light conditions. For scale, the resolution is between 600 and 900 meters per pixel. Again, notice the moon's long striations and craters, some of which are stacked on top of each other. I've seen a lot of photos of Ganymede, many of which I've covered previously, but I'm floored by the level of detail Juno was able to capture in such low light conditions. Interestingly, one of the most surprising discoveries from the mission came not from the orbiter itself, but from Hubble. Yes, that Hubble. Allow me to explain. You see, to support Juno's exploration of the Jovian moons, NASA asked Hubble to monitor Ganymede's ultraviolet signals. Ganymede has an atmosphere, albeit a very thin one, and one of NASA's goals was to find traces of oxygen they long suspected was hiding there. Nearly everyone expected to find plenty of oxygen based on previous analysis of the moon's ultraviolet emissions, but much to our surprise, Ganymede's atmosphere had very little oxygen in it. What they found instead was a whole lot of water vapor. This discovery led to a significant revision of our model of Ganymede's atmosphere, and could suggest that water vapor might even be present in the atmospheres of icy bodies throughout the solar system. After visiting Ganymede, Juno made its flyby of Europa on the 29th of September 2022, which gave the probe a gravity assist that shortened its orbit to 38 days. Here is a dramatic image from the flyby, taken at a distance of 351 kilometers. It shows a portion of Europa just north of the equator. What I find extraordinary here is the day-night boundary known as the terminator. The deep shadows really accentuate the ridges, troughs and craters that riddle the moon's surface, showing it in almost three-dimensional relief. Scientists think that Europa, like Ganymede, harbors a vast ocean beneath its icy exterior, but new findings suggest there could be a lot more going on than the simple ocean crust model would have you believe. What do I mean by this? Well, hold that thought as we study the next image. This photograph was taken by Juno's Stellar Reference Unit camera and shows a zoomed-in portion of Europa's surface. It was taken during the moon's night from a distance of 412 kilometers. With a resolution of 256 meters per pixel, this is the highest resolution image that Juno took of Europa. At a glance, your first thought might be, what am I looking at? Well, what you're seeing is a heavily fractured region of Europa's surface, crisscrossed with grooves and ice ridges. And that oddly shaped dark patch just to the right of center could yield important clues as to what's behind this geological complexity. Scientists believe this darkened area shows an eruption occurring below the surface ice. The thing is, Europa's icy shell is over 10 kilometers thick. Imagine the pressure needed to penetrate so much ice. However, a new paper published by American Astronomical Society proposes a groundbreaking new theory, pardon the pun, with a different explanation. According to the paper's authors, Europa's cryovolcanic activity shows evidence of brine reservoirs trapped within the icy outer crust. This would mean that, far above the moon's subsurface ocean, there could be lakes of high salinity brine that slushes about, expanding the surrounding ice like a balloon and bursting through on occasion. It's a compelling theory, but to prove it, we may have to wait for the European Space Agency's Clipper mission, which will reach Europa sometime in 2030. I know that's 4 years away, but it's not too early to mark your calendars. Let's head back to Jupiter. You see, while Juno was paying visits to Ganymede and Europa, it also solved a big mystery, one that goes back more than 40 years. When the Voyager mission first visited Jupiter in 1979, the probes detected mysterious flashes in Jupiter's atmosphere. Scientists assumed that these were lightning flashes similar to those we see on Earth, meaning water would have to be present in all its states: solid, liquid, and gas. Given what we know of Jupiter's atmosphere, this would put the storms at least 45 kilometers below the visible cloud tops. However, Juno disproved this theory, and the truth is stranger than we imagined. Juno's Stellar Reference Unit camera saw something weird: nighttime flashes at a far higher altitude than we thought possible. Given the incredibly cold temperatures at this altitude, reaching below -88 degrees Celsius, scientists deduced that the storms were made of ammonia water-based clouds, a phenomenon that doesn't exist here on Earth. In these strange and violent thunderstorms, the ammonia acts like an antifreeze, forming a solution of 2 parts water, 1 part ammonia, that remains liquid despite unimaginably cold conditions. And apparently, as these thunderstorms produce powerful lightning strikes, they are raining down massive hail made of water ammonia slush, an unusual precipitation that scientists are calling mush balls. Jupiter is a strange planet, and the more we learn, the stranger it gets. Juno completed orbit after orbit, and over time it shifted its attention away from Ganymede and towards Io. Io is Jupiter's 3rd largest moon, and the most volcanically active world in the solar system. In 2023 and 2024, Juno bravely made several close flybys of Io, coming within about 1,500 kilometers of the surface of this hellish Jovian moon. During these encounters, Juno snapped its first ever images of Io's northern latitudes, mapped Io's surface, and captured photos of ghostly plumes rising above the horizon. Io is dotted with hundreds of volcanoes across its surface. Massive fountains of molten lava, some towering dozens of kilometers into the sky, paint a violent portrait of Io's volcanic prowess. The moon's relentless volcanic fury is driven by tidal heating, as immense gravitational forces stretch and squeeze Io. An easy way to conceptualize tidal heating is to think of Io like the rope in a game of tug-of-war caught between the pull of Jupiter's powerful gravity and the pull of neighboring moons Europa and Ganymede that orbit farther away from Jupiter. As Io orbits the giant planet and experiences the tug and pull from other nearby moons, it stretches and flexes, generating friction and immense heat in the moon's interior. This heat is what sparks the volcanic activity across Io's surface. Juno's microwave radiometer instrument pierced through the atmosphere, gathering critical data to craft detailed maps of Io's landscape, revealing that it has a relatively smooth surface compared to Jupiter's other Galilean moons. It's theorized that this smooth surface is the result of a constantly renewing surface. Tremendous heat and pressure within Io keeps much of its subsurface in liquid form, and that magma is constantly escaping to the surface to relieve the pressure, whether by filling in craters or bursting through cracks. These frequent lava flows could erase impact craters and cover floodplains with smooth lakes of lava and glassy obsidian-like rock that reflects sunlight. One striking image from Juno's 60th flyby on the 9th of April 2024 captured Io's south polar region. While this image was taken from 16,500 kilometers away from the surface, you can still pick out several dark spots across the moon, many of which are lava-filled cauldrons and volcanic depressions. Several of Io's volcanic eruptions were also captured by JunoCam, the mission's visible light camera. On the 15th of October 2023, JunoCam spotted a plume over the Prometheus volcano just below the terminator line. The Prometheus volcano is one of the most prominent volcanic features on Io, having been seen repeatedly in images of the region taken by Voyager, Galileo, and the Hubble Space Telescope, and now by Juno as well. Voyager 1 was the first to observe Prometheus in 1979, a volcano made up of an enormous cauldron and lava flow, with a tall plume of 50 to 100 kilometers that rises above the end of the lava flow. On the 3rd of February 2024, Juno caught another 2 plumes in one photo from just 3,800 kilometers above the surface. These might have been 2 plumes from one gigantic volcano, or 2 volcanoes that were just close to each other. JunoCam also gave us a better look at 2 landmark features on the Jovian moon. One of these was Io's largest volcanic depression, Loki Patera. This 200-kilometer wide area has a lake filled with cooling magma just reaching the surface, rimmed with hot lava and dotted with unnamed islands. The flyover imaging of Loki Patera provided spectacular reflections of the lake, suggesting that it, along with other areas on Io, is smooth as glass. In addition to visible images, the spacecraft used its Jovian Infrared Auroral Mapper, or JIRAM, to study heat sources on Io, an instrument that was originally designed by the Italian Space Agency to monitor auroras on Jupiter. This instrument was able to pinpoint significant heat sources across the moon and provide measurements of thermal emissions radiated in infrared wavelengths. Because of this, NASA scientists with the Juno mission were able to identify another lava lake on Io. This one is called Cause Patera. Visible and infrared images were combined from 2 of Juno's flybys, one in 2022 and the other in 2023, to create a map of Io's volcanic activity. Here, data from the space probe's infrared mapper was overlaid onto JunoCam's images of Io, which you see as spots of red, yellow and bright white color. The data on the left was collected from 80,000 kilometers, and the data on the right was captured at 58,000 kilometers. To put that into perspective, the infrared data in these images has a spatial resolution of about 20 kilometers per pixel and 15 kilometers per pixel respectively, meaning these hotspots represent absolutely massive areas of volcanic activity. And for the first time ever, 30 years worth of data was combined to create a map of volcanic activity on Io. This map shows the varying power output of hotspots where magma has erupted out from the moon's interior. Notably, the map shows the presence of polar volcanoes. While it does not confirm the presence of a magma ocean beneath Io's crust, this information certainly does support that possibility. During the flyby, on the 15th of October 2023, Juno also captured the first of its kind close-up images of Io's northern polar region, taken from 11,700 kilometers above the surface. Because NASA's Voyager and Galileo missions did not gather complete images of this area, Io discovered 3 never-before-seen mountains in the northern latitudes. Those mountains are circled in red in the upper part of this image from JunoCam, near the line dividing day and night known as the Terminator. These close flybys also gave us a look at another stunning feature on Io, Steeple Mountain. A striking peak shaped like a cathedral spire, Steeple Mountain is a unique landform that rises between 5 and 7 kilometers above Io's surface. Can you imagine what it might be like to watch the sun rise behind this jagged summit? Or the views if you could climb to the top? But perhaps one of the most awesome moments in Juno's evaluation of Io came on the day we saw its biggest ever eruption. On the 27th of December 2024, as Juno was doing a flyby of Io, lights lit up all across the moon's scarred surface. Numerous volcanoes out of Io's 400 erupted simultaneously across a 65,000 square kilometer region, releasing the most energetic volcanic event we have ever seen in our solar system to date. Their synchronized fury seemed to confirm that they were all connected to the same lava channel. And yet, even more curiously, not all the volcanoes within this region erupted, indicating that some may have been connected to a different lava channel network. Io may or may not have a magma lake beneath its surface, but it certainly seems to be quite spongy down there.
and it is dealing with a planet-sized version of heartburn. But Juno did not just look at the Jovian moons during its mission extension. It looked again at Jupiter too, getting up close and personal to Jupiter's turbulent atmosphere, peering into its swirling storms and mesmerizing stripes. Remember, as the largest planet in our solar system, Jupiter is a colossal titan, stretching nearly 70,000 kilometers across and 11 times wider than Earth. It could fit 1,000 of our Earths inside. In fact, some individual storms on the surface of Jupiter are so big they would swallow up our entire home planet. As part of its mission, Juno ventured ever closer to Jupiter's North Pole with each passing orbit, allowing its MWR instrument to capture a series of images from different orientations. This combination of images allows for improved resolution and analysis of the polar storms at different wavelengths. And this data revealed that not all polar cyclones are created equal. For example, this series of images depicts Jupiter's northern polar cyclones in 3 different wavelengths. From the left, these images show microwave, visible, and infrared light. The infrared image, which tells us about the heat in the atmosphere, and the composite visible light image both depict Jupiter's northern polar storms as well-defined and of similar size. However, the microwave image tells a different story. Take a look at this storm, for example. It shows a notably reduced emissions intensity compared to other storms, despite appearing distinct in the other 2 wavelengths of light. The MWR instrument records the glow of Jupiter's atmosphere in microwave light, with 6 different radio channels that each peer deeper and deeper below the cloud tops. The highest frequency sees the top of the cloud cover, while the lowest can see up to 320 kilometers below. This microwave imaging enables Juno to pierce deep into Jupiter's atmosphere, beneath what we can see with the naked eye. Take another look at the polar cyclones in microwave light. These 2 storms at the 4 and 6 o'clock positions were about the same size as the other nearby cyclones in visible light, but they show more intense microwave signatures than the other storms, which indicates that these extend at least 100 kilometers beneath the top of the clouds that we see. Also intriguing is that the central cyclone is clear in both the visible and infrared images, but in the microwave light, the cyclone all but disappears. This indicates that the central cyclone's subsurface structure may be very different from the surrounding storms. On its 61st to 66th flybys, in my opinion, Juno captured some of the most spectacular images of Jupiter's folded filamentary regions in the northern hemisphere, offering a detailed view of the chaotic clouds and cyclonic storms. In this region, the same zonal jets that are known for creating Jupiter's famous banded cloud patterns break down. And without these jets, the planet's clouds swirl into turbulent patterns that rapidly evolve over the course of just a few days, like a choreographed dance that's always changing and never ends. This unforgettable swirling canvas of blues, whites and browns is something I could stare at for hours. And for planetary scientists, these beautiful and sometimes terrifying images hold clues about Jupiter's weather patterns and atmospheric dynamics. On the 7th of March 2024, Juno's 59th perijove gave us a rather special set of images of Jupiter. Here we see the planet's famous atmospheric belts and swirling storms, including the Great Red Spot. But if you look a little closer, a charming detail is revealed. Jupiter's tiny moon Amalthea is visible in these 2 images. At just 84 kilometers wide, Amalthea is shaped like a potato, as it lacks the mass to pull itself into a sphere. This tiny moon circles Jupiter inside Io's orbit and takes roughly half of 1 Earth day to complete an orbit. Curiously, Amalthea holds the title of the reddest object in our solar system, its crimson surface radiating more heat than it absorbs from the distant sun.
Perhaps this is caused by electric currents that are induced within the moon as it orbits within Jupiter's magnetic field. Or maybe it's caused by tidal heating from Jupiter's gravity.
And of course, Juno captured some lovely images of Jupiter's classic bands on its later orbits,
including this one from the 54th perijove on the 7th of September 2023, and this one taken during the 62nd orbit on the 13th of June 2024. Another objective of the Juno mission is to quantify the amount of oxygen and hydrogen molecules, which make up water, that are present in Jupiter's atmosphere, to help us understand more about the planet's water abundance. Jupiter was likely the first planet in our solar system to form, and it contains the majority of gas and dust that didn't become part of the Sun, which means it is also a critical piece of the puzzle of our solar system's formation. Additionally, the planet's water abundance has implications for its meteorology, like how wind currents flow and what the planet's internal structure is like.
Luckily, Juno is helping us answer these important questions. MWR data from these later orbits has helped to gauge Jupiter's water abundance,
showing roughly 3 to 4 times the elemental abundance of hydrogen at the equator as compared to the average concentration of that element found in the Sun. This supports the idea that water ice material may have been the source of heavy element enrichment during our solar system's formation. If this is the case, it would mean that as Jupiter formed, it accumulated not only hydrogen and helium, but also heavier elements contained in water ice material, which was not abundant in the early solar system.
However, further measurements from Juno showed a surprisingly low water abundance in Jupiter's core, raising new questions as scientists expected to see more water in the core if water ice were indeed the primary source of Jupiter's heavier elements. So for now, the formation of Jupiter remains a mystery that scientists are still trying to sort out. Now, all good things must come to an end. Juno was originally intended to be shut down in 2018. Even Juno's extended mission was supposed to finish by September 2025. And yet, there is a little twist at the end of the tale of this indefatigable probe, because, against all odds, it is out there still. There are many question marks over this. You see, due to political events, the US government was shut down at the time that Juno's mission was supposed to end. This left the fate of Juno in a strange state of limbo. News pundits at the time speculated that the probe had possibly been shut off, and we just hadn't been told, as this had always been the plan. Juno was supposed to be deorbited at the end of its mission into Jupiter's atmosphere as a way of making sure that it never accidentally impacted Jupiter's moons. We hoped to one day investigate those moons for signs of life, and NASA was keen not to muddy the waters. So, by all reason, with the deadline passed, Juno should now be shut off. And yet, Juno lives still. NASA has been cagey about the fate of Juno, but just a few days prior to me writing the script for this video, they posted an article about Juno data and how it was helping to narrow down the exact thickness of Europa's ice shell. Much of the article refers to prior data, and yet at the end comes the captivating words, Juno will carry out its 81st flyby of Jupiter on the 25th of February. So, for a probe that was intended to solve the mysteries of Jupiter, it seemed that Juno has become one instead. Its fate is somewhat unknown. NASA had faced the threat of sweeping budget cuts last year, and Juno was one of the missions at risk of being cancelled, shut down to avoid its running costs. But Congress seems to have rejected this idea, passing a bill that roughly maintains NASA's budget at previous levels. So perhaps missions like Juno will get a new lease of life. Perhaps it will simply be allowed to drift slowly into Jupiter's warm embrace, allowing it to capture a closer look than ever into those ammonia clouds, and eventually that fuzzy core. Who knows how long that process will be. But for now, it is out there still, doing science, still going strong. Waste not, want not, after all. For this resilient probe, as long as it is still functioning, perhaps not even the end of its mission will be enough to stop Juno from discovering Jupiter's secrets. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving even when they're sponsor free. It's the reason we can research deep into the topics we love without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.